chapter 4, I don't remember. Anyways. So we stopped it here last time talking about these models, these languages that seem to be weird, but apparently they are still there, people are still aware of. Yes?
But I noticed that all of them, they're used as a joke, they're not like actually used.
Nice, very good. That's very good. Okay, so what is the most weird one that you've seen?
Or chicken and Shakespeare.
Any other?
Chicken. Also white space. Yes.
Was there anything outside this list? Have you seen? No? Okay, interesting. Very good. So yeah, it might be a joke. I haven't personally looked into them yet, but they seem to be weird, honestly, by name. Okay, so today we're gonna look more into the development, like what happens inside our computer, our machine, how actually our code gets translated into something that's executable. So if you remember, we talked last time about, did we talk about the source code, pipe code? No?
No, yes, we did.
We did, right?
Yeah, we talked about how the computer translates.
Okay, perfect. So we said usually we type our code in like source code mostly, which is the high level language, right? And we're having here our binary code, which is mostly written in zeros and ones, right? And we said this is the fastest usually when it runs on the machine side, right? That's why when we move towards low level language, you get to see that the performance and the cost of complexity gets to be less because you execute without any translation, right? So that's simply what the compiler does. But again, there are lots of stages here in between. So if you remember last time, we were talking about high level, middle level, assembly, machine, and binary. And we gave some examples on it like Java, Python, Perl, Shell, C, C++, let's say Intel. We have here machine code, which is read by the operating system directly in the series of zeros and ones, which is again similar to the binary pattern. But again, this is how it goes. So writing things that are human readable, then executing it as instructions that might simply be between the high level and the low level, right? And we end up with the low level, which is machine language. So this diagram represents it in the best way possible. Compiler simply translates your high level language to what we know as an object code, or what we refer to as bytecode. Remember, this is written whether in C++, could be in CP format, or let's say in Java, which is .java file extension. Then bytecode, which is simply class, right? And again, it happens here after a compilation stage. Then I have here a linker, which is simply turning your bytecode into binary code, which is nothing but executable files, right? So again, this is just a sample, moving from .java to .main to .executable. All right. So how the compiler works and how the interpreter works. So which one you think needs the other one? Does the compiler need interpreter, or the interpreter needs a compiler?
Compiler needs the interpreter.
So the compiler needs an interpreter. What does the word interpreting means?
It's line by line.
Yes, it is line by line. So here we're trying to understand the code line by line, right? Now when you have this full understanding, you can say that I understand the entire file, right? So this is what the interpreter does. And this is what the compiler does. Okay? So here this is independent executable file. Here, direct code execution, which is line by line, but this is whole code. And we have here real-time error detection. Here, the error detection comes post-compile. So after this stage is over. Yes, Farah.
دكتورة ما فهمت ليش بيحتاجوا بعض، أنا اللي بعرفه إنه اثنين نفس الشيء واثنين نفس الوظيفة، بس مثلا واحد لبايثون واحد لجافا.
No, okay, interesting.
ولا شو؟
So a compiler needs to tell you at the very end a full report, okay? So it tells you, for example, you have these number of syntax errors, right? Now, how would it tell that this is happening? It goes over something like a dictionary, okay? So all these syntax keywords are saved in a dictionary, a big one, like F statement, like for loop, let's say, like while, and so on. All these keywords that we commonly use, class, implements, extends, all of them. Then it gets you a full comparison. Is the code you're writing, line by line, actually matches any of these keywords I store in my own dictionary? So interpreter does grasp and understand, line by line, okay? So what are you trying to do here? Okay? Are you trying to open a new statement, let's say for a for loop? Are you building a header for a method? This is what the interpreter does, okay? At the very end, so it makes like a line by line check. This is okay, this is okay, this is okay, this is not okay, this is not okay. This final report is what's sent later to the compiler. So the compiler can tell you, okay, you have 3 syntax errors. One at this line, one at this line, one at this line, right? How does it know? It's the interpreter, okay? Now in modern IDEs, typically you no longer have a compile and a run button. So you get to see same button and all these features are embedded within. So once you click run, it gets you the interpreter, then the compilation, then the final execution stage, okay? All right, so here, again, the compiler leads to bytecode, right? But then the bytecode with the use of interpreter is what makes it possible for you to get the machine code or the binary code. Okay? This is just for your info. You don't need to worry much about it. But typically here we're talking about possible skills that if you have across all these coming years, that would make a robust profile for you as a developer. So starting from the package of programming languages, you can start having web application, development skills, database management skills, version control and development methodologies, which we talked about already if you remember, Agile, Scrum, version control like Git or GitHub, for example, databases like SQL, MySQL, and so on. Here we have Python, Java, Script, Kotlin, C#, PHP, Swift, Ruby. For web, we have HTML, CSS, JavaScript, React, Angular, Vue, Node.js, Ruby, and so on. And of course, what you're taking so far in data structures, including arrays, linked lists, trees, graphs, different sorting algorithms, search algorithms like quicksort, merge sort, binary search, and so on. Of course, you need to integrate this with some management and orchestration tools, similar to Docker or Kubernetes. Then you need to also learn the skills of testing and debugging, whether unit testing and what kind of debugging tools you can use for this. Again, this is for your info. You don't need to worry about this, okay? But it's good to keep this in mind for later advancement. All right, now let's look into development as an activity list. And I will start here with the easiest phase. So we all know coding, right? So what's coding? It is simply the process of picking a language, building your own code, considering some standards. As we talked about it, IEEE is one, right? We have, for example, ISO and so on. So this is the most important phase. But again, once you code and once you're done, that's not the end. A whole review process starts, right? Eventually, we've taken some techniques of reviewing code before, if you remember any.
Test cases.
Yeah, of course. I mean, yeah, but more like detailed one. So while coding, how do you review your code?
As in, like, make it better?
Yes,
Refactoring?
similar, exactly. Refactoring is the end result of the review, right?
Yeah.
So when you notice something is off and then you recommend possible changes and enhancement. But how would you get this review stage done?
Debugging?
Hmm?
Debugging?
No.
We efficiency, like, depending on how efficient the code is.
Yeah, how would you tell this is efficient or not?
Do we
By the runtime.
Users assessment?
Before, now we're still coding.
can't we ask someone else to check
We're
our
close, very close.
Check with the developers, maybe? As
You're
peer
very
pro-
close.
Peer programming. Peer review?
Thank you. So pair programming is one technique of reviewing the code. Remember when we said there is a driver
yes.
and there is someone who
Navigate.
guides and advise? Exactly. Again, we will see lots of other techniques, but this is only one. And of course, this can lead to continuous integration. So we can tell, okay, this unit is now ready and we can move towards the next one. Now, our entire development here works in accordance to the diagrams we built in design phase, right? But again, how would we let a huge team work together? Let's assume we're having 10 people working together on one project, like you do, for example, in SE201. Your teams of 5 or 6, I don't know, right? How would you split the work? How big your project would be? What is the biggest number of files you've dealt with so far? 7 files in one project? 8?
Yeah, maybe like 6 or
6 or 8? Up to 10? Nice. How did you work on these 10 files as a team?
Each one like gets 2 files.
Each gets 2 files. Okay, so you do it offline and then you integrate?
Yeah.
Is that the case? Interesting. Have you never experienced working online with each other?
No.
We didn't have time.
GitHub. Yes.
Okay, so there are some tools that are meant for this purpose, okay? They can let everyone join the same repository and it gets to be shared among everyone. If you do a change your side, it reflects automatically my side, right? So GitHub is one, but if many people actually see it a bit complex, so you can still find lots of other replacement. But again, this is mainly used to manage our source code. And of course, this applies to all other possible documentations.
When
Yes.
we did the IEEE, whenever someone answers the
Yeah.
question, it answers for everyone.
Yeah?
Like it shows the answer before even submitting it.
Interesting.
Yeah.
Okay, cool. All right, so we have here the unit testing. So unit testing comes after this stage of review, right? So here, we let all our developers test each and every unit separately. What do we mean by unit? This could reflect a use case, right? So like login, I don't know, registration, logout, each of them is a separate unit. So we do test-driven algorithm. We go for automation sometimes. So how many possible input the user might have that would be safe? How many possible other inputs that if you put on the system, it might crash, right? So many of the times, we don't depend on testing it manually, just giving it a random set of inputs and testing how it responds every time, right? Automation is very important that you can keep on pushing data, even if you don't know what's happening, right? You just keep on pushing data using code, and you keep, it's like a brute force sort of approach, right? You keep saying, okay, when will it crash? So if that happened, this indicates that this unit still needs more time to review and adjust. Of course, you keep on fixing bugs and refactoring whenever needed. Then we have documentation, which is very critical phase. And we spoke about it, if you remember before, we said some of the processes won't allow you to have like reliable sort of documentation. Do you remember? What was it?
Incremental.
The incremental process, exactly. Because again, the level of changes is a lot, right? And your exact focus is not on keeping it full readable, but rather it's mostly on how to satisfy the end user or the stakeholder. So in terms of code readability, when reading, when let's say you put lots of comments in your code, making sure that even if you are visiting this code again after 1 year or so, you can still understand what's happening. Then we also have tutorials. So by tutorials, I mean, how would you train the user to use this software, right? And user manuals as well. Sometimes it holds technical guides that this could be actually meant for developer. So it can tell them, for example, how to type in errors, how, let's say, to resolve it, and so on, right? So typically that's how everything starts. You start by planning, then you code, you build, you test, you release, you deploy, you operate, you monitor, right? Now under coding, we know that we can use the version control tools. We develop our own source code. Here we keep on developing and automating. We do here a quality control check. And we keep on integrating and, of course, continuous delivery and deployment as you move on. Now for operation, again, this is similar to the orchestration tools like Kubernetes or other tools similar. Anyone here used GitHub before? 1, 2, 3. Okay. So again, the idea here is having multiple developers. They all have access to the same repository. What's a repository? Heard of this word?
It's like the main interface we all get to work on.
Close, close. So a repository is nothing but a folder, right? But this folder is simply shared by everyone in this project, right? Or multiple people. So they can all have access to it at the same time. They can choose to make changes. They can choose to extract changes if needed. So this is similar to how it looks like. We have something we call master repository, which is the main one. And below it, you might see some other branch repositories. So here, once you're done with the change, this is commit command, which means save my work, right? Then every time you requested, this is simply a pull request. Every time you want to upload it so people can actually see it, this is a push command, okay? Now in general, we do split our coding steps into 3 main ones. We code, we unit test, we integrate, right? So here we write our actual code based on our design document, and there should be good mapping between both. So it can't be the case that I ignore entirely my design and I start coding from my own head. If you're having a class diagram, you have to stick to it, right? Again, why? Because these diagrams have been approved by stakeholders. So now if you introduce a code that's written in a different way, this might not be the one that's satisfying. Now we go through unit testing, which means we're verifying the functionality of every unit in our code. Again, do test login, do test the registration, the sign out, the cart, and so on. Then take these components together and go for Integration, make sure that these two can work together in one piece of code. Same for third one, same for fourth one. So we end up here with something similar. Okay. So here, I try to turn my own design into a tree-like structure, okay? Now, what is that? What is here actually? What do we represent by these blocks?
Tree.
It's tree, and every block here represent what? A unit, exactly. It's a unit, right? So these units could be looked into as small components. Why do I have gray ones and white ones?
Empty spaces and buildings.
What?
Maybe the gray represent like empty units.
Look again. Yeah.
The gray have
Because they have
Thank you. So gray ones are those that could be split further into more units or components. See, this one has children. This one has children, and so on.
Dr. Why, but for what purpose?
So here we're just seeing, that's a very good question. So why? We need to first define the big task, then know how to split this into smaller tasks. All right? So the main goal here, you want to know, is it a leaf node or it's still a node that could be broken down? That's what we do when building any plan for our project. One of the key components that you will need to develop is something known as Gantt chart. So in a Gantt chart, we will have to reflect processes similar to Scrum, let's say. Remember, we said we need to have a list of tasks where each of them could take how many days? Do you remember? Up to come?
Up to 4 weeks.
Up to 7 days, right? So this means that this scope of this work is not actually huge. Something to be done in 1 week, right? So here it means I reached the level where I cannot break it down anymore, right? So it is already manageable within 7 days. And already one person can handle. Once you reach the leaf node, it means it cannot really be broken down any further. Now, when I have this, it gets easier for me to try to see the relation between these units. So which one takes me to which one, right? So this one is dependent on this one is dependent on this, and so on. And you can see that some of them can run in parallel if that's the case, or possibly disconnected. So, please.
The one that has the arrow is dependent on the one that
Yes,
doesn't.
here the entire diagram tasks are relevant. Yeah. But you can still, I mean, if you don't put this, for example, it means I can start these two in parallel, right? But these two will be initiators. Now this is wrong, because ideally speaking, we start from a single root. So you can't actually start with two in parallel. So you might break down these dependencies at lower levels, but not the highest one. So in general here, we're trying to have coding components divided into small, manageable units referred to as chunks. The tasks are assigned based on the experience to every team member. So who's good in art, take this. Who's good in design, take this. Who's good in sound effects, take this, right? Now define the split depths and the task relation, as we explained here. Then we focus on quality and efficiency. So this is very interesting. How do we implement? So let's assume now we are in an organization and we're trying to build a software. And you have one of 4 possible options to tell me that this new software is ready. And let me give you this constraint. I already have a software that's up and running since 2000. Okay, so this has been how many years? 25 years. I'm addicted to this one. I know each and every single bug inside, right? So I know how to use it. Then you came to me saying, okay, we're offering now a new update, 2025. Now there are 4 possible ways to do it. So these are implementation methods that we can use. One that we call direct cutover. Second one is parallel. Third one is phased. Last one is pilot. So what is the direct cutover? That's my old software, right? So I'm gonna tell you, okay, stop it. The day after, you're starting the new software. So by cutover, it means what? Stop, then start immediately. No gap in between, which is this one, right? So this is my old system. This is my new system. Who can tell me what's the drawback of this one? Again, look into it as a user. Yeah.
I mean, like usually the features, maybe there was better features in the older one that might not be accessible in the newer version. And like for example, like you said, like the developer, maybe they know the older model much better, so they'd have to relearn the entire system again.
Okay. So we're talking about features. We're talking about familiarity, right? What else? How long do you think will take people to adapt to this new software? Long or short time? So the same moment they start the new system, they will know how to use it?
No.
Okay. Did you all experience the switch from the classroom to planner
Yes.
or not? You all did? How easy was it? Did you struggle a bit in the beginning? Okay. So here, we usually, or ideally speaking, and it depends of course on how complex is the software, but we would require a period for training, right? This training is not necessarily physical. I don't have to gather all students in one venue and tell them this is how to use the software, right? It can be made in different possible fashions, one of which could be sending a user manual or PDFs and documents, exactly. So they came up with the parallel approach. So again, just to give you an example on the direct cutover, let's imagine an ATM machine, okay? So you made a transaction at 11 p.m. You went to the ATM machine, okay? You know how to use it. You withdraw your money. You went back home. It became 12 a.m. Then they decided to renew the entire software of the ATM machine. So from version A, it became now version B. And you woke up the next morning على نفس ATM and you find this new software. So this is cut over, right? In one night, moving from system A to system B. And you have no direct access to this previous one anymore, right? Like when you do actually the update on your phones, do you all receive it?
Yeah.
Can you retrieve back to a previous update? No. This is cut over, right? We switch off, we turn on. So we moved here to the parallel algorithm. So parallel tells you, okay, so this is